Think of the capacitor as a reservoir that stores energy in the form of an electric field, and its capacity is defined by the amount of charge it holds divided by the voltage across it. On the other hand, the resistor acts like a bottleneck, limiting how easily electrons can flow through the circuit, with its resistance being the ratio of voltage to current. When combined, these elements work together to control the exact rate at which electrical charge moves. This is the fundamental principle behind creating an electronic clock. When a capacitor is connected to a voltage source, electrons begin to flow from the negative terminal to one of the capacitor plates. As these electrons accumulate, they create a charge that generates a voltage across the capacitor, which opposes the supply voltage. As this voltage approaches the supply's electromotive force, the current reduces gradually until it stops completely. When we look at discharging, the power supply is bypassed, which means the capacitor itself becomes the only source of electromotive force. Because of this, the stored charge in the capacitor pushes electrons back through the resistor. The current, or the rate at which charge flows, is directly proportional to how much charge remains in the capacitor. This means that as the capacitor loses charge, the push driving the electrons decreases, causing the discharge to slow down over time. So essentially, the less charge there is, the weaker the push, and the slower the capacitor releases its stored energy. As a capacitor charges over time, the voltage across it increases gradually and approaches the maximum supply voltage, V0, following an exponential curve. Initially, the voltage rises quickly, but as it gets closer to V0, the rate of increase slows down until it nearly levels off. Similarly, the charge stored on the capacitor also rises over time, starting rapidly and then slowing as it reaches its maximum charge, Q0. Both voltage and charge versus time show this smooth, asymptotic approach toward their maximum values during the charging process. Meanwhile, the current flowing into the capacitor decreases over time, starting at its highest value and dropping towards zero as the capacitor becomes fully charged. Here, we see how the voltage, charge, and current change over time during the discharging process. The voltage and charge both start at their maximum values and gradually decrease towards zero as time passes, showing that the stored energy is being released. Meanwhile, the current starts at a negative value and increases towards zero, reflecting the direction and gradual reduction in the flow of electrical charge. The time constant, represented by the Greek letter tau. It's calculated by multiplying the capacitance, measured in farads, by the resistance, measured in ohms. The time constant tells us how long it takes for the voltage, current, or charge to drop to about 37% of its original value, or to rise to about 63%, depending on the situation. On the graph, you can see the voltage starting at its initial value and gradually decreasing over time. The point where it reaches 37% of that initial voltage corresponds to one time constant. As the capacitor discharges over time, the charge on it decreases exponentially. This is shown clearly in the graph, where the charge starts high and gradually approaches zero as time passes. The equation describes this behavior quantitatively, stating that the charge at any time is equal to the initial charge multiplied by an exponential decay factor, which depends on the time, capacitance, and resistance in the circuit. Here, we see how voltage, charge, and current change over time during the discharging process of a capacitor. The voltage and charge both decrease exponentially, starting from their initial values and gradually approaching zero. This reflects the capacitor releasing its stored energy. The current, on the other hand, also decreases exponentially, but begins from a negative initial current, showing the flow of charge out of the capacitor. These behaviors are captured by the equations, where each quantity decreases according to an exponential function with a time constant defined by the product of resistance and capacitance. When a capacitor charges from a DC supply, the voltage across it increases over time following the curve shown. At one time constant, which is the product of resistance and capacitance, the voltage reaches about 63% of the supply voltage. After 4 time constants, the voltage is approximately 98% of the supply voltage, and it virtually equals the supply voltage after around 5 time constants. This behavior is described by the formula shown, where the voltage across the capacitor at any time is the supply voltage multiplied by 1 minus the exponential of negative time divided by the product of resistance and capacitance. When measuring rapid changes in voltage, relying on human observation introduces a significant delay, about 0.2 seconds, which causes uncertainty in the timing and accuracy of recording these quick drops. On the other hand, using digital data loggers addresses this problem effectively. These devices sample data at very high frequencies, capturing hundreds of precise time and voltage points every second, allowing us to accurately map the exact curve without the limitations of human reaction time. The graph shows how the voltage or charge decreases over time, and you can see that the slope, or gradient, of this curve changes depending on the voltage level. In fact, the gradient is inversely proportional to the input voltage. It's hard to measure it accurately because it's constantly shifting. To better analyze this data, especially when dealing with exponential decay, we need to find a way to transform this curved graph into a straight line. This would make measurements simpler and allow us to calculate changes more directly, without constantly dealing with these changes in slope. The question then becomes, how can we adjust our approach or manipulate the data to reveal that straight line? To make the exponential decay easier to analyze, we use a logarithmic transformation. By taking the natural logarithm of both sides of the equation, we turn the exponential equation into a linear one. This means that instead of dealing with a curve, we get a straight line on a log linear plot. Specifically, the equation becomes ln v equals ln v underscore 0 minus 1 over cr times t, which matches the form of a straight line, y equals c plus mx. Here, ln v corresponds to y. ln v underscore 0 is the intercept c, and negative 1 over cr is the slope m. This makes it much simpler to measure and understand the relationship, since straight lines are easier to work with than curves. What we do here is transform the original voltage versus time curve by taking the natural logarithm of the voltage values and plotting them against time. This converts the exponential decay into a straight line. The slope of this line corresponds to the negative inverse of the time constant crossing. By measuring this gradient accurately, we can calculate the time constant CR simply as -1 divided by the gradient, which gives us a more reliable and straightforward way to analyze the decay process. First, we have a simple circuit with a resistor and a capacitor. When the switch is closed, the voltage across the capacitor starts to decrease exponentially over time, shown by the curve on the graph. This decay follows the equation V equals V0 times e to the power of negative t divided by CR. To make analysis easier, we take the natural logarithm of the voltage, which transforms the exponential curve into a straight line, simplifying the determination of the time constant. The slope of this line is -1 over CR, which is very useful because it directly relates the measurable slope to the product of the resistance and capacitance, giving us a unified way to analyze the system and extract the time constant clearly and efficiently.